di hatiku. Assalamualaikum, very good morning to everyone. Yang berbahagia Profesor Teknologis Dr. Muhammad Azlan Muhammad Ishaq, our distinguished speaker, lecturers and fellow students. Ladies and gentlemen, first of all, it is my pleasure to be the chairperson for this professorial lecture series. My name is Puan Faiza from Chemistry Unit, Center of Foundation Studies, University Teknologi Mara Cawangan, Selangor, Dengkil Campus. To bless our program today, I would like to invite Muhammad Faris Wajdi bin Yusri Effendi to recite the dua. Faris?
Al-Fatihah. A'udzu billahi minasyaitonir rajim. Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin hamdan yuwafi wa yukafi malidah. Ya Rabbana lakal hamdu kama yanbaghi li jalali azimi sultani. Allahumma ansurna syu'urana nahjihna wuyudina wa rabbit qulubana bil karamah wahsin akhlaqna bi nuril hidayah wa sabbit qulubana bi kulli riyayah. Allahumma zukna ma'abati biyuni waj'alna min sajidin biwajhikal karim. Allahumma ja'alna bil afiyati was salamah wafisna bit taqwa wal istiqamah wa aizna min mawajibal qadamah waghfir lana warhamna wal walidayna wa aman ahbana wa ahsana ilaina wa liman kana haqqan alaina bi rahmatika ya arhamar rahimin. Allahumma aftah alaina hikmataka wanshur alaina min hadaini rahmatika ya arhamar rahimin. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina adzabannar. Subhana rabbika rabbil izzati amma yasifun wa salamun alal mursalin walhamdulillahi rabbil alamin.
Amin, amin. Thank you, Faris, for the dua. Okay. On behalf of the Chemistry Unit, Center of Foundation Studies, we wish to extend our warm welcome and thank you to Yang Berbahagia Profesor Teknologis Dr. Muhammad Azlan Muhammad Ishaq, who are willing to share his expertise and knowledge to our science students here in Pusat Asasi. A brief introduction about our speaker. Yang Berbahagia Prof. Teknologis Dr. Muhammad Azlan Muhammad Ishaq is a professor at the Chemistry Department, Fakulti of Applied Sciences, University Teknologi Mara, Arau Campus. He also holds a position of Deputy Rector at Division of Academic Affairs. His research interests are in green chemistry and instrumentation. For today's lecture, Prof will cover subtopic 1.9 and 1.10 from our topic 1, matter and stoichiometry, and subtopic 2.1 from our topic 2, electronic structure of atom, periodic table and periodicity. Without further ado, let's kickstart today's session by inviting our speaker for the first session of our lecture. Please welcome Yang Berbahagia Profesor Teknologis Muhammad Azlan Muhammad Ishaq. Okay, Prof, the screen is yours.
Thank you, Dr. Faiza. Thank you very much. Okay, how's everyone today? Can everyone hear me?
Good. Yes.
Clear? Clear?
Clear.
Line saya tak berclear tadi tu. So sorry. Okay, thank you very much and thank you to Chemistry Unit, Center of Foundation, Asasi, UiTM. Actually, I'm also from Asasi, but 30 years back, in 1988. So I'm your super senior. Okay, I thanks to Chemistry Unit for inviting me to give to share a little bit. Actually, subtopic regarding the chemistry chapter under the foundation chemistry. So can I share my slide now? Actually, this slide was given to me by Dr. Faiza. Wait now. So slow. Wait. Can everyone see the slide?
Not yet, Prof.
Here is mentioned you representing to everyone. I also cannot see my slide.
But I can see this slide, Prof.
Uh-huh.
So
How about the students?
Yes.
can.
Yes.
Can? It not appear on the Google Meet, but I can click. So can I start now?
Yes.
Yes, Prof.
Yes, Prof.
Okay. Under the topic of concentration expression, what do we know about concentration actually? Okay, concentration. But here, he asked us by end of this topic, students should be able to calculate the concentration of solution involving molarity, percent by mass, percent by volume, molality, and mole fraction. Okay, in chemistry, we can see here there are more than one unit of concentration. But in common sense, in daily usage of concentration, normally we just use, in Malay we say as kepekatan, is it? So kepekatan is actually, in English, most people using is molarity, molar. Okay, actually molarity is come from scientific word. Okay, molarity is from scientific word. Okay, scientific word. Okay, we can see molarity, molar. Okay, from the word molar. But nobody knows until they learn chemistry. So as a chemistry student, we should know there is more than one unit of concentration beside molarity. Okay, another unit which is come from percent by mass, percent by volume. So when we talk about percent by mass, percent per. So it consists of two units. Again, similar to molarity, it also consists of two units. Okay, I will explain after this what are the two units. Okay, percent by volume, of course, involve two units, except for this one is volume over volume. This one, mass, okay, weight over weight. And then the other one is molality. This is very, very seldom we use. It looks similar to molarity, but slightly different, of course, in terms of the spelling. Okay, molarity. But here, still involve two units, but per unit compared to this one is referring to volume. This one per here is referring to mass. Okay, and the last one, we should know the term mole fraction. This is the most common one. Okay, so we hope that by completing this subtopic regarding concentration, students should be able, and of course should know the first one, the term of the different type of concentration, and also know how to calculate. Okay, basically when it involves this different type of units, mostly we have to calculate. Of course, why? Because we need to prepare solution. Okay, so we need to prepare solution. Sometimes people asking us, please prepare this molarity of concentration, please prepare this by volume, or please prepare this by weight. Okay, sometimes we heard the concentration unit comes into solutions such as ppm, part per million, part per billion. Okay, million and billion, and so forth. So the ability to calculate this different type of molarity will give us many application in our daily life. Okay, for example, in our daily life, do we aware that when we drive car, okay, when we drive a car, in a car normally, as for safety reason, most of the car or automobile nowadays, they will be fitted with airbags. Do you know airbags? Kan? Airbags. Do you know how the airbags functioning? It's actually chemical inside there, and airbag, the bag is flipped into very small, tiny size, and the reaction behind the airbag is actually chemical reaction between I think some of the reactant when being heated. Okay, when the car being heated, the electric will automatically ignite this chemical reaction to occur in a very, very fast way, so that the chemical will explode. So when it's explode, it will turn on the bag. Okay, airbag. Okay, that's why we need to really calculate the precise amount of the reactant when it react. Okay, some of the application nowadays involve this ability to prepare most of the reactant involved in most of the pharmaceutical area, okay, green chemistry, ecological, or even in certain chemical product. Okay. Okay. Before we go further, let us look at the concentration expression. Okay. There are three main important keywords. Okay. Normally, when we involve some idea or some what we need to learn and new things, always bear in mind we need to know the keyword first. Okay, of course we read sometime from the article. Okay, it explain how to, it explain everything, but always bear in mind while reading the manuscript or while reading the text, always our hand always have a pen and then some papers. Okay, please jot down. Okay, we never learn, because this is not literature, because we learn science. Science actually we see, we say, and we think. Sometimes we write, or sometimes we verse simultaneously. So always make sure that these things happen simultaneously, so as we much easy to remember. Okay, in this concentration, the three main keywords are, the first one is, which one? Can anybody help me? There are three words here, capital letter here: solution, solute, solvent. Which comes first? Can anyone help me? Please. Please.
Solution.
Are you here?
The solvent.
Which come first?
Solute. Maybe.
Which come first? Is it solvent first?
Solute.
Solvent.
Solvent first. Some say solvent, some say solute.
Solute.
Some of you say solute, some of you say solvent. Is anyone say solution?
Solution.
Is it right solution? Can you imagine this morning you try to prepare, let's say, tea or coffee? What first you prepare in your glass or mug? What first thing you put in your mug? Water, okay. Some of you put water first. Some of you put coffee first. Kan? Betul tak?
Yes. Yes.
So, the first thing first, either solute or solvent is considered correct. Okay, this thing first need to be prepared. So when you mix these two, so the product is solution. Okay, the product is solution, provided the solute is totally dissolved. So, and then we can call solution. Let's say if you put too much sugar or too much coffee, you try to stir it so many times, you will leave behind some of the sugar undissolved. That one is still called as solute. It's not solution. Even though you prepare the solution, it's not 100% solution, partial. Okay, that's why when we learn concentration, we need to know how much solute, how much solvent need to be prepared, need to be added to form a good solution, which is we call homogeneous mixture of solution. Have you ever heard homogeneous? Anyone? Have you ever heard homogeneous?
Yes.
What is it? What is
Yes.
Maksudnya
it? In a
sebati.
simple way, is homogeneous actually.
Maksudnya macam sebati gitu.
So lawan dia. Have you ever heard heterogeneous? So against homogeneous is heterogeneous, meaning that if we put solute in not a proportion amount with solvent, there will left behind heterogeneous mixture of solution. That is not considered as homogeneous mixture of solution. That's why when we learn concentration in chemistry, we need to involve another parameter which is called stoichiometry. You know stoichiometry? Kan? Stoichiometry.
Yes.
What does it mean?
Yes.
Stoichiometry. We are not learning physics, we are not learning mathematics, but now we are learning chemistry. Portion of chemistry is concentration. It looks simple, actually very simple. Okay, if you don't know, it become difficult lah. So that's why we need to learn from the fundamental. So we need firstly know what it is the keyword and know which come first, which come later, and the importance of the keywords. Okay, so in concentration in chemistry, when we try to produce solution, we need to know exact amount of solute to add with exact amount of solvent. The exact amount of these two entities, when it react together, in a common sense we stir together. Okay, in chemistry we say we react together, and this just enough amount of these two entities, which is called stoichiometry. Okay, stoichiometry, and then we can produce homogeneous mixture of solution. Okay, so in order to produce solution with certain concentration, okay, that involve ratio. Okay, ratio. Why we say ratio? Just now, can you imagine if we put certain amount with excess of solute or with less amount of solvent? Okay, so when we mix these two, people will ask, these two things when we mix together, there is certain ratio. Kan dalam bahasa Melayu kita kata bau banyak sudu nak bubuh kan, bau banyak air nak tambah. So ada nisbah dia. So in common sense, we already talk about the ratio. Same as in chemistry. When talking about chemistry, when we try to prepare solution, we need to have certain ratio. Okay, certain ratio of solute. Okay, even though we have certain amount of solvent. Okay. Okay, I'm not sure whether this sentence quite appropriate of solute to the volume of solution. Actually, to the volume of solvent. Okay, solution concentration ratio or amount of solute to the volume of solvent. Okay, we need to have certain amount of solvent. Normally, people doesn't care about how much solvent is this. They have, okay, because they just put certain amount of solute. They measure solute. They never measure solvent. When they didn't measure the solvent, that's why it comes another parameter which is called limiting reactant, excess reactant. Because these two is considered as reactant. Solute and solvent is considered as reactant. This is the final part. Okay, these two are reactant. When solute dissolves in solvent, these two reactant. Can you imagine these three keyword when you put all together in a chemical reaction, okay, reactant A plus reactant B produce product. So you can imagine solute plus solvent produce solution. Okay, so there is certain amount being added within these two reactant to produce solution. Okay, so when we talk about ratio, okay, when we talk about ratio, it's actually the ratio between solute and solvent only. Okay, we have to calculate, okay, the ratio between solute and solvent. Okay, it's simple when we talk about when we try to prepare tea or coffee or Milo. Okay, we just measure in terms of sudu teh kan, ataupun sudu besar kan, 3 sudu, 4 sudu. It becomes simple. It also becomes simple in chemistry when we talk about concentration. When we try to prepare, we need to know how much amount of solute. So when talk about solute in chemistry, when involves so many type of compound, okay, solute is a common name. So in specific name, it can be compound. Okay, so we need to measure how much compound need to dissolve in certain solvent. So we have this relationship. Okay, so concentration in chemistry representing by M, capital M, molar. Okay, or we talk about molarity. So it gives us the ratio between solute and solvent. Okay, and this molarity comes when we mix these two, solute and solvent, in a certain ratio. But because this involves chemistry, we no longer use sudu ataupun camca. So we need to use another unit. So this unit which is called mole. Do you know mole? Okay, 1 mole. Okay, regardless of how much you take, but we need to normalize it back into moles. Okay, because we want to standardize the concentration in molarity. So the molarity says it has to have the unit of solute in mole divided by amount of solvent that you use. And this solvent we use in liter. Even though you use only 10 milliliter, we need to normalize it back to liter. It becomes simple. Let's say 10 mil, you convert to milliliter, you just divide by 1000 milliliter. It becomes 0.001 liter. So this is the conventional unit of molarity. So by now, we should understand that in order to produce certain concentration of solution, we need to have certain amount of solute in mole unit. How much solvent when we write back into the sentence, it becomes mole per liter. Either we write as mole L apostrophe minus 1, or we write mole stroke liter. It's almost the same. Okay. This representing molarity. Okay. It says here that concentration of we representing the unit mole per liter as by this symbol. Okay, X is again two symbol approaching this X. Okay, so there are many applications of solution in chemistry, movie solution chemistry, as I mentioned just now, in pharmaceutical, in producing airbags for automobile, and so many things, because they need to measure exact amount of reactant to be reacted in order to produce what target product they're preferring. Okay, you can find more in Google. Of course, you can Google. Okay, you can read some articles. You just start application of solution chemistry, thousands of or millions of application you can see from the Googles. Okay. Okay. This is representing before and after. Okay, when you put certain amount of solute and you add solvent, finally all solute dissolve in solvent to produce solution. Of course, the volume from the initial become increase. That's why M times V, okay, from the initial is equivalent to M times V2. When we put unit for the M1 V1, we can have the mole actually. M unit for M is mole per liter, we times liter. So liter will cancel per liter for the initial, same as liter will cancel liter from the concentration for the final. We are actually have the same mole of what? Same mole of what? Can anyone help me?
Solute.
Same mole of what? Solute, yes. So can you imagine, okay, we didn't add more solute, we just add solvent. So eventually the volume increase, so we produce solution. The amount of solute is still the same. Okay, the amount of solute is still the same. That's why always remember when we learn chemistry, we know chemistry, let the chemistry guide us for life. Tahu tak? Faham tak? Orang kata kencing manis kan? Kita makan 10 gula, kan? Kita buat satu kopi, we make cup of coffee, kita bubuh 10 sudu gula, ni cup kopi ni, and then kita tambah air 1 liter. Can you imagine? Of course, the dilute kan? But if you drink only 1 cup, in a jug, you produce 1 jug of coffee with 10 sugar. But if you drink one cup, it's okay. But if you drink the whole solution, meaning that you are taken into your body 10 spoon of sugar. Okay, that's why we need to understand that even though you have the beginning amount of solute, it doesn't matter, but you need to control your solute in order to have certain concentration. Even though after you drink solution that contain 10 spoon of sugar, you say that after that no problem, I can drink 2 liter of water. Of course, but in your body already receive 10 spoon of sugar. So be aware that, okay? That's why we need to understand concentration. Before and after, when we calculate mole, before and after, for the solute, it's actually the same, okay? Provided we consume all the solution, okay? Okay, another relationship between stoichiometry and concentration here, we give an example, okay? When we talk about stoichiometry, it's actually relationship between reactant and reactant. Sometimes you also refer to stoichiometric relationship between reactant and product. Okay, that's why we need to have standard equation so as we can calculate to get a proportion to produce certain product that we need. For example, here, calcium bromide. Okay, when it dissolves, it will dissociate into calcium ion and bromide ion. Okay, we try to balance this equation. So calcium 1 mole, 2 mole in terms of compound, 2 mole in terms of ion. Okay, this is product, this is reactant. So if we have 0.1 molar calcium bromide, meaning that also have, because the mole is the same, we are comparing the mole. Remember, when we have two situations, even though the solute before and after the same and the volume before and after different, we are calculating the mole of solute. Okay, mole are the same. That's why when we try to compare, okay, in front of each entity in front of each compound or atom or ion, it gives you stoichiometric number, okay, integer number, representing mole of the entity. Here we have 1 mole calcium bromide, produce 1 mole calcium ion, produce 2 mole bromide ion, okay? This mole is actually the same as this one. We are talking about mole, okay? So when we try to we need to compare the same mole. And to help us here, calcium bromide 0.1 molar. Of course, 0.1 molar, 0.1 mole per liter. Okay, this concentration. If we have the same concentration, because the mole is the same, so as for the bromide is times 2. Okay, because it has 2 mole. Okay, when we compare the same amount of mole, so we have proportion of 2, we need to times 2. In BM we call as perkadaran kan, 1 mol berkadar 1, kalau 2 berkadar 2. Okay, that's why proportion is very important in stoichiometric in order for us to determine certain concentration for the unknown. Unknown meaning that when the question asking us to calculate, because they will give data on certain reactant, but asking us to calculate another reactant. It doesn't matter as long as the data is completed, so we can calculate and then we compare. And this comparison, which is called proportionate, we try to proportionate. Kita akan kadarkan dengan what we have data given to us. Like this one, we have this as standard. So when the question asks us what is the concentration of bromide, okay, we don't have the data, but we can compare. We can proportionate with calcium bromide by talking about mole. Okay, always remember we are comparing the same mole. Okay, people might ask, this is different mole. Here is talking about the same mole, but here is different mole. Calcium bromide, of course, different mole, but all together in a same beaker. But when we talk about mole, of course, we have different type of species, but it appears in terms of mole. Yalah, when talking about mole, can you imagine? Mole here in Malaysia, mole in maybe in US is the same. That's why we need to have the standard unit. Okay, we need to agree that 1 mole for bromide is molarity mole bromine in a molar mass. See? So let in conventional when we say 1 kaki kan 12 inci. So we need to accept 12 inci as the unit. We cannot accept 1 kaki 13 inci lah. How about people in US? They still stick to 12 inci because world has accepted as 1 kaki, okay, as 12 inches kan. Same as in chemistry, okay. When we talk about mole, even though we are comparing this different type of species, it doesn't matter. But when we try to calculate back in terms of its weight, yes, then we have to times with the molar mass of that species. Okay, same as this one. We are not talking about. We don't know what type of mole solid is that. We're just talking about amount of mole. Okay, if in this solution contains different type of mole of species, okay, A, B, C, mole A, mole B, mole C. So the same as when we put solvent, it become certain solution of mole A, mole B, mole C. Okay, it doesn't matter. Even though here it doesn't show to us there are more than 1 mole type of species. Okay, so we talk about chemical reaction, always bear in mind, okay, even though we have different type of species, sometimes species here, so many type of species here, reactant A, B, and C produce product A, product B, product C. It doesn't matter. All you have to do is just balance the chemical reaction. Okay, just balance the chemical reaction, which is called stoichiometric. Okay, stoichiometric meaning that amount of reactant will react a quantized amount of reactant to produce a specific amount of product. Okay, so we can start to compare and can start to calculate amount of each reactant and also amount of each product to produce same amount of proportionate mole. Okay. Okay, from now, boleh faham ke?
Boleh.
Yes.
Susah ke payah ke?
Boleh.
Belum lagi.
Belum lagi. Senang je kan? Okay. Let us look at the concentration expression. Can you remember the first slide I showed just now? Okay. There are so many types of unit. Now we start to go one by one, the concentration expression. For the first one, beside molarity, okay, we use the main concentration of unit being used in IUPAC. They use molarity, mole per liter. We also need to know other type of concentration in a conversion. Just because of this occur because of the solute, the solution, sometime in a different form. Okay. When we talk about molarity, of course, it also sometimes comes in different form, but we try to standardize it to have unit that being mostly accepted. But yet, in certain cases, we can also convert from the standard unit mole per liter into various type of concentration. Because if you can see here, the main unit of ratio between solute and solution is still the same. Okay, solute over solution, solute over solution, solute over solution is still the same. But the difference between these three is actually in front of it. When we talk about mass percent, when we start talking about mass percent, we need to have mass of solute, mass of solution. Okay, when we put percent, we need to time 100. Actually, we don't have to have percent here because when we time 100, it's actually percent lah. Okay, so when we talk mass percent, this ratio times 100. Okay, this ratio times 100. Okay, when we talk about percent volume, okay, volume over volume. Okay, when we talk about volume, in front of it should be volume over volume of what? Solute over solution. Okay, and when we have to have percent, of course we just time 100. Okay, just simple like that. Next one is see here, weight over weight. Solute comes in form of weight. Okay, solution, okay, also in terms of weight. Sometimes people asking, why are we make it so difficult? Why we want to have weight over weight, whereas solution mostly in volume? Yes. Can we aware that? Do we aware that? Okay, solution comes with the in English we call ketumpatan, density. You know density kan? Mass over volume. So by having this unit, we can manipulate. And that's why from the mole per liter, people start to manipulate. Okay, in terms of weight over weight, weight over volume, volume over volume, so as they have different variation of concentration. Not just because they want to have different concentration, just because sometimes they have solute in a form of mass. They have solute solvent in terms of solid. They have to dissolve, they have to calculate, they have to convert. So in final, they need to convert all the mole per liter into specific concentration, what they have done on the solute or solvent. Okay, the third one is percent of mass per volume. This one slightly different from the both two. Okay, mass over volume. Okay, so when we talk about mass, so the first one, of course, mass. Always fix the solid over volume. Always fix. Okay, solid over solution. Okay, so it become mass of solid per volume of solution. Okay, per volume of solution. Okay, one example here. It give us 32% weight over volume. So we automatically should know that 32 weight is gram. Okay, see, 32%. Percent meaning that the whole volume is 100. Normally, the most simplest way we take 100. Very seldom people take 45 milliliter, or sometimes when we take less than 100, we have to normalize back to 100 just because to have it in form of percentage. So for this example, it gives us 32% weight over volume of sugar solution. Okay, 32% weight per volume of sugar solution. So when we read this statement, or when we read this concentration, okay, this is type of concentration. Okay, 32% weight over volume. So we translate it into 32 gram sugar, which is solute. Okay, see, solute. Which one? Weight over volume. This one. So 32 gram sugar, okay, solute, per, this one per percent is 100. So per 100, if talking about volume, we need to put unit in volume. So 32% weight over volume, meaning that in 100 ml of solution, it contains only 32 gram sugar, okay, being dissolved in the solution. Okay, so in other words, 32% is actually 32 gram sugar per 100 ml of solution. Okay, one of the most seldom unit being used here is molality. Looks similar to molarity. The difference is L and R. So here, talking of molality, is actually mole of solid per 1 kilogram of solvent. Molarity, mole of solid per liter of solution. Okay, very simple. Just different between the unit of solvent. Liter, kilo. Okay, liter and kilo. So molality, mole per kilo. Molarity, mole per liter. Okay. Okay, last one, we also need to know mole fraction. Okay, just now when we mix more than one solute in certain solvent and dissolve, sometimes people ask us, what is mole fraction of A? You mix with B. Okay, sometimes it's total fraction, mole fraction. So the mole fraction is a fraction of mole of one component in the total mole of the all component in the solution. Okay, when we talk about fraction, there is no unit. Not to say there is no unit, we already cancel. When we divide with certain the same unit, okay, when we divide the same unit, mole, total mole. Okay, mole, it will cancel. That's why there is no unit, or we call as unitless. Okay, unitless. Of course, total mole, of you just total up all mole involved to form that solution. Here one example. Okay, this question asking us to calculate the volume of 10.5% by mass. See, 10.5% by mass soda contains 78.5 grams of sugar. When we see the concentration, automatically we need to know that this is unit of concentration of certain solution. Either by mass, by volume, whatever. Automatically we need to know that this is concentration. Another one, when we give to us sugar, automatically we know this, of course, solute. Okay, amount of solute given to us with amount of concentration. Another unit given to us is density. Okay, of course, sugar combined with solvent. This solvent, when we mix, it will have certain density because this is not, it's not purely water. Okay, it's not purely water. So to calculate this, okay, take all the data given to us first. Okay, we have here 78.5 gram sugar, which is the solute. You can put solute if you want. Asking us to calculate the volume. Calculate the volume. Okay. Normally, if data given to us, normally we know that we need to calculate first. The first thing first, try to calculate. Try to do some operation on the unit given to us. Okay. Provided we put in a proper way so that we can cancel the unit. That's the most important thing. In chemistry, there is one chapter that we call dimensional analysis. Okay, dimensional analysis. You can see here. Although we look at one direct operation, but it's actually we can divide into two operations. To those who are quite not familiar with straightforward operation, you can do stepwise operation. First thing, you have to do the operation between these two first, and then try to do in a proportionate way. Okay, perkadaran. Try to do in a proportionate way, perkadaran, and you can get the answer in a sequence order. Okay, if you can see here, given to us, okay, 100 gram solution. Okay, in 100 gram solution, this is talking about percentage. So 100 gram solution, percent 100. Okay, if by mass, a gram. Okay, so we just translate this concentration first. 100 gram solution, in 100 gram solution, it contains 10.5 gram sugar. Okay, see, we just interpret the concentration given to us. So either or, we can say as 10.5 gram sugar contained in 100 gram of solution. That's why when we construct proportionate sentence, we can put either way. Okay, we can put either way. Nak tak belah mana pun boleh. Bergantung pada apa yang kita nak calculate. Okay, another data given to us is the density. We can also write the density here, 1.04 gram per mil into here. In other words, 1 mil solution is contain about 1.04 gram. That's how we translate. From here, we translate to here. From here, we translate to here. Why? Because we want to use this for next calculation. Make it become easier. Normally, people translating from given data given into here because they want to put in one short operation. This is called one-step operation. Okay, provided the unit is correct. Okay, to solve this problem, okay, 78.5 gram sugar times 100 gram. Okay, this percentage over 10.5 gram sugar. You can use either or. Okay, times 1 min over dia punya its density. Make sure that you can cancel the unit, eventually giving you the correct unit. One, if you want to have volume, you bear in mind you have to have volume here. In here we didn't see the cross, kan you cross, you potong G sini, gram sini, you potong di sini gram. Okay, cancel this one, cancel this one, cancel this one, cancel this one. Left behind is mil. Yes, correct. Okay. Okay. To those familiar with this one-step process, you can go by this type of process. But normally, to those people who are not familiar with this, you can go stepwise. There are only 2 steps in order to produce this answer. Okay. You can discuss evaluate before after this. Okay, another example. Okay, calculate the molarity and molality. Molar. Okay, remember molarity, mole per liter, molality, mole per kilogram. it doesn't matter. If you can get the molarity, you can automatically convert to molarity, okay? Because we have the density. So not much a problem. So this question asking us to calculate the molarity and molality of solution prepared by mixing 17.2 gram of ethylene glycol. This is solute, okay? Okay. Please calculate molarity and molality of solution. Always bear in mind, solute, solvent, solution. Okay, you are asking to calculate the molarity. Let us focus on molarity first. Okay, so you were given 72 gram of ethylene glycol with 0.5 kilogram of water. This is solvent. Okay, always bear in mind, density of water is always 1. Okay, so if the solution, if the question giving to us is 0.5 kilogram, meaning that it's the same as 0.5 liter. So you can calculate the molarity the same as you calculate the molality, either or. Okay, to make 515 milliliter of solution. Okay, and then another question, determine the mole fraction. Okay, first thing first, we convert into standard unit. Not to say that milliliter is not standard, but when we talk about molarity, the unit is mole per liter. So we need to convert milliliter into liter first. Next, try to calculate how much the solute in the solvent. It's already give the solvent, it's already give the solute. So just calculate to know how much mole this ethylene glycol being used. Okay, so this amount of solute times with mole of water. Mole of ethylene glycol. If we want to know the amount of mole of being used, we need to divide by molar mass of ethylene glycol. You can calculate, okay, carbon times 2, hydrogen and oxygen, and finally you can get 0.277 mole of ethylene glycol being used, combined with 0.55 liter of water to produce this type of concentration. Okay, so much easier for us calculate either or. You can have the first one with molality just now. Okay, because we already calculate liter, we produce molarity first. In exam, normally if you calculate molarity, it doesn't matter as long as the question asking molarity first or molarity, it doesn't matter. You can calculate either or first. Okay, you can put molarity first because given to you is already kilogram, and yet you convert to liter, it's still the same. Okay, and then you have the molarity, molar, 0.5 kilogram of solution. Okay, this is solution. Okay, another thing is the difference between molarity and molality. This is liter of solution. Kan? Solution, huh? Solution. See? This molality, liter of solvent. See? The difference between molarity and molarity. So mole divided with solvent. Mole divided with solution. Mole per liter solution. Mole per kilogram solvent. So the unit becomes slightly different. That's why molarity is not the same as molality, even though the same amount of solute being dissolved in the same amount of solvent, because we are referring to different type of unit. Okay. Next, asking us to do is the mole fraction. So get mole of water, and then you have to have mole of total. Total up, you can get total mole of solute plus solution. So fraction, you just divide by the total. More you can get this amount. Of course, very, very small. Okay, 0.2, talking about 0.2 divided by 28. Okay, so far so good. There is one question. Okay, if you can calculate how to write this first. and we can calculate this later. Question 1 asking us to calculate the mass of solute and mass of solvent from each prepared solution. There are 3 questions from question 1. 1 to 5 gram of 1% weight over weight sodium nitrate. Okay, you can write down first, write the answer. You need to see the process how you get the answer. Okay, second one is 1 gram of 0.115 molar. Okay, so be careful. Just now molar is talking about mole solute over kilogram solvent. It's not solution. The last one is 1 to 5 mil of 0.1 molar sodium nitrate. Given to us also density of solution. Second question is calculate the amount of water in gram need to be added to 5 gram of urea. Okay, urea is the solute, water is the solvent, in preparation of 60.2% by mass solution. Okay. You want us to stop first or we continue? Nak break sekejap ke?
Boleh? Take 5.
Take 5. Try buat soalan tu dulu. While waiting for 5 minutes, try buat soalan yang given to you ada di checkpoint 17 ni. Question 1 dengan question 2. Jawapan ada situ. Okay. Kalau siapa nak pergi toilet boleh lah. Take a break. Semua student berapa, Dr. Faizah?
Maaf Prof, kelas ni daripada S01 hingga S010. Satu kelas lebih kurang dalam 25 orang.
Oh,
Kelas
combine class lah.
Ya, combine 10 kelas.
Oh, 10 kelas?
Cumanya satu kelas tu wakil 9 orang saja yang masuk dalam Google Meet.
Oh.
Bakinya tengok daripada YouTube Pusat Asasi.
Maknanya total the whole foundation asasi ni
dalam untuk sains dalam 2000 lebih saya rasa, tak silap saya lah, 2000 lebih sains.
Maknanya this is sains hayat.
Ya, betul. Sains hayat.
Ramai lah, 2000 lebih.
Ramai. Kami ada grup sampai S58 kalau tak silap saya, ada 58 kelas.
Itu dia. So how dia punya loading for each lecturer to tackle semua student?
Sem ni loading kita agak rendah sikit lah, 12 saja ATS-nya.
Oh. Tapi mostly lecture, lab.
Kami handle 3-3. Lecture, lab, tutorial.
Itu dia. Memang heavy lah. 18 tahun kan lebih.
Boleh lagi lah.
Okay.
Student baru masuk minggu ketiga ni Prof, jadi agak macam baik lagi lah. Baru week 3 ni.
Mode of teaching now, is it 100% bukan kan?
Face to face dah 100%.
Face to face kan? So any problem regarding COVID-19 punya issue?
under control lah. Ada tu ada tapi under control.
Ada kan?
Ada.
Actually nota tu Dr. Aisyah bagi dah hari tu. Saya 2 hari demam.
Okay.
Saya buka semalam baru saya buka. Sebab saya bukan apa sebab pergi ambil booster yang kedua sebab appear dalam Mas Sejahtera. Saya just isi fill up lah. Bila fill up jadi dia buat appointment on the 26 pagi. Ambil lah. Ambil siang okey lagi. 10 malam habis satu badan sakit.
Yang sebelum ni okey lah.
First dose tu pun macam tu juga sebenarnya. Saya boleh kata semualah sakit. Bulan 4 hari tu pun saya dah kena COVID dah sekali. Sama je, dia macam alhamdulillah kita boleh dapat vaksin. Dia jadi badan ada imun lah. Tapi dia tetap ada juga dia punya tanda-tanda tu, sakit badan, sakit sendi. Cuma alhamdulillah tak teruk lah, tak macam kata apa, susah bernafas tak ada lah. Dia macam demam.
Ringan-ringan je lah simptomnya.
Ringan-ringan je. Cumanya agak suspend nak ambil yang kali kedua ni bila kita tahu the same symptom kan. Tapi dia tanya kawan yang doktor, dia kata ambil je, dia kata dah free ambil je. Jadi saya pun dengan berat hati ambil jugalah. Jadi menanggunglah 2 hari demam.
Tak apa, dia nak boostkan kita punya immunity juga, Prof.
Itulah. Tak ambil jugalah kata. Sampaikan klinik tu tanya, pasal apa encik nak ambil? Dia tanya, saya heran. Saya kata sebab keluar dalam Mas Sejahtera. Yang 50 age and above kena ambil. Jadi saya datang sajalah. Dia kata biasanya yang ambil booster ni selalunya nak pergi overseas. Encik nak pergi luar negara ke? Pula. Dia kata macam, daripada stop ambil cucuk patient masa nak pergi haji hari tu. Jadi bila ada yang baru ni, dia prepare based on booking. Dalam hari tu saya tengok dalam 6 orang je yang masuk booking.
Orang macam tak sangatlah nak ambil.
Ya. Saya tanya nurse tu, kebanyakan orang positif ke negatif? 90% negatif. Dia kata setakat dapat complete dose 1-2 is okay. Booster pertama tu just because dia ada urusan lain, nak pergi luar negara ke. Kalau tak ada, dia pun tak ambil.
Okay.
Mostly macam tu.
Sebab hari tu kan KJ macam dia cakap kan kena ada 3 juga kan.
Ya.
Itu kau orang ambil kan. Kali ketiga, kali keempat orang tak nak ambil dah kot.
Tak mau ambil dah. Macam. Okay student. Boleh kita sambung? Can we continue?
Boleh.
Okay, let us look at the first question. Try check with your answer. Okay. The first percent sodium nitrate, okay, X. Solution given to us 1%. We just put here X and then rearrange to get back mass of solvent. Okay. Same goes for the B. Okay. Finally, you should get 298.9 grams solvent. C1 is the mass, even they're asking us to calculate mass. Okay. Given to us is mole, molarity and volume. So normally data given to us, okay, normally they're asking us to do something, okay, provide something, and then we start to operate. Okay, mass solution, mass solvent. Question number 2, percent mass. Okay, percent mass from the same relationship. Okay, put back all the data, rearrange the data, you should get mass of water. Okay, another question from checkpoint 18. Okay, the density of 2.45 molar, okay, mole per liter aqueous solution of methanol is 0.976 gram per liter. Okay. calculate the molality, okay, of the solution. Okay, this is concentration of the methanol solution and the concentration of methanol, gram per mil. Okay, this gram per mil is actually representing concentration of methanol in terms of weight over volume. Is total solution. Okay, 2.45 molar is the total solution. Okay, given to us also concentration of the solute, which is methanol. Always bear in mind, when we talk about solute, normally people will remember solute is solid. Okay, in chemistry, it doesn't mean solid. It can also be liquid. Okay, as long as these two liquid is miscible. They use the term miscible, melarut between the both phase. Water is solution, solute is solution. Okay, so these two phase is miscible, so it can dissolve. That's why methanol here is liquid. Solution final is liquid. It's no longer solid. So that's why diverse concentration here we use is weight over volume, volume over volume, or weight over weight. Given also here is molar mass of the solution, which is the methanol. From the data, we can calculate first the data given to us here. We can get the gram of methanol. Okay, 2.45 mole per liter. Okay, 2.45 mole per liter. Okay, this is 32 gram. And you can get in terms of gram. So by having the density, so finally we can get the mass of the solution. The mass solvent. Always remember this molarity. Okay, molarity. Solution. Molar solvent. So the question asking us to calculate the molality, molar. Okay, so get all the unit properly put in the each of this operation. So mass of solvent. Okay, you can get mass of solvent. Convert it into kilogram. So by having this unit for solvent, you can get the molality, mole per kilogram of solvent. That's molality. Okay, it's not difficult to remember. Always bear in mind when they give two units with different meaning, molarity, molality. Always try to think of what's the difference between these two units. Always write it down. Molarity, mole per liter. Okay, mole of solute per solution. Molality, mole per kilogram. Mole of solute per kilogram of solvent. So if you have this in your mind, you can easily remember. And of course, when you given to you any type of unit, you can convert it into what unit the question asks you to do. Okay. Okay, we go to the solution stoichiometric. Just now, what we learned is in general term of unit of concentration up to preparation of certain solution or solvent with different type of or various type of concentration unit. So now we try to look into the solution stoichiometric. Okay, stoichiometric involving solution. Okay, learning objective of this topic is to solve problem related to solution stoichiometry. Okay, example of reaction that involve solution stoichiometric, there are 4. Okay, or we can say that situation we have 4 situation or reaction in different form. The first one is under gas formation reaction. The other one is gravimetric analysis. We can see the gravimetric and gravity. Metric is unit. So what are we measuring is by the support of gravity. We need to measure the weight. So gravimetric analysis is referring to weight amount of product being produced. Sometimes even we produce weight, but the question asking us to measure the reactant. Or sometimes we measure the reactant without knowing how much produce the product. So we need to measure the product. Another situation, this solution stoichiometry being used is on the acid-base titration. Okay, acid-base titration involving a solution in a stoichiometric amount of reactant. Okay, when certain amount of reactant, normally they use oxidation method mixed with reduction method to produce product. So neutralization produce product. So the fourth example of reaction is redox reaction. The same as acid base, because acid base is combination of acid with base, and then finally you can get the neutral product. Even though redox, although not considered directly of acid base, the way of reaction between the two reactants normally is similar as acid base titration. Okay, so there are four phenomena lah. We can say phenomena, or we can say any type of reaction involving solution stoichiometry. The first one, we look into the gas formation reaction. When there are no gaseous reactant, the formation of an insoluble or slightly soluble gas provide a driving forces for a type of reaction that we call a gas formation reaction. Okay, for example, when excess of sulfuric acid react with X gram of zinc, 500 milliliter of hydrogen gas is evolved at STP, standard temperature and pressure. Always remember, when we dealing with gas, normally scientists have to measure the amount of mole, okay, because talking about solid and liquid, they will use molar mass of the element to convert it into mole. But we talk about gas, it's hard to measure the weight or volume unless they need to measure at a certain standard temperature and pressure with a standard amount of stoichiometric, and then they can measure regardless any type of gas, provided we put the standard condition. Okay, so meaning that when we try to measure gas, it has to be measured at standard temperature and pressure. This is at stoichiometric stage. Okay, here when talk about reaction, okay, when talk about reaction, and this reaction must be stoichiometric, always bear in mind we need to have chemical reaction. Okay, chemical reaction. Normally we need to translate, okay, or we need to translate from the sentence into chemical reaction. This is how chemists work. Okay, sulfuric acid, make sure the formula is correct, not to say HSO4. Okay, sulfuric acid, make sure the compound is correct, H2SO4. React with zinc, zinc is solid. Okay, ion combination, so produce zinc sulfate. For example, this equation is given to us, much easier lah. So in future, sometimes it just give to us the question only. So student need to work out the chemical reaction. Kejap. Okay. Okay, here they ask us to calculate the excess of sulfuric acid, because in liquid normally this is in excess amount. Ya, nanti saya telefon balik. Saya ada mesyuarat lah. Jadi saya telefon balik lah. Okay. Sorry. Okay. the question asking us to calculate the excess of sulfuric acid, because sulfuric acid in an aqueous liquid form, normally this is in excess amount. In chemistry, when the two reactant reacting, they sometimes involve another form that we call as excess. The other one is limiting. Excess amount, limiting amount. Okay. The excess amount, of course, normally liquid. The limiting amount normally is this solid. But we need to calculate to prove it, whether it is excess or limiting reactant. Okay, back to this question. It asks us to calculate, okay, excess of phosphoric acid with X gram of zinc. This is used in excess, but we don't know how much zinc is used to produce zinc sulfate. And make sure that this equation is stoichiometric. In other words, the amount of mole of the reactant react to produce product is equivalent in terms of mole of each of the reactant and product. In here we can calculate lah. Hydrogen 2 here, zinc 1 mole, sulfate ion, sulfate ion. So that's why in front of each reactant and product, it also all have the same amount of mole. Okay. Okay, bear in mind. Just now, can you remember the two diagram before and after? We are calculating actually mole. Okay. So that's why when we have different type of species, we also have to calculate, or we also have to compare, or we also have to proportionate them in terms of mole, regardless of the formula, regardless of the compound on the reactant or product. Okay, always remember that. So hold in our mind that we can compare either whether the amount of reactant, regardless of reactant is different type, okay, product is different type, it doesn't matter as long as in front of each species is integer representing mole of each product and reactant. Okay. Okay, back to this question. Here we have 500 ml of hydrogen gas. Given to us the product amount, 500 milliliter of hydrogen gas at STP. So at STP is actually, we need to determine the mole of the gas. Okay, mole of hydrogen. 1 mole STP is 22.4 liter. Okay. 1 mole of any gas at STP, the measured is amount 22.4 liter. Okay. So this is a standard unit for STP or any gas. So we can use this for hydrogen. So with times amount of hydrogen produced is actually 500 ml or 0.5 liter of hydrogen produced is actually 0.0223 gram mole of hydrogen only. Okay. Okay, now question is, why are we so concerned to convert milliliter to mole? Can anyone help me? Why are we so concerned to convert milliliter to liter and finally to mole? Can anyone help me? Because we want
To find mass.
Yeah, we have to do this because we want to proportionate. Ingatlah, we want to proportionate. Kita nak kadarkan dia. Kita nak buat perbandingan. We want to proportionate. Now we only have hydrogen. Okay. As I said earlier, we can compare, we can proportionate any of these species in this chemical equation by having its mole only. So anyhow, any group, we need to calculate, we need to convert any data given to us into mole. Okay. So here, because this is gas, we need to convert it into gas and then finally get the mole. Once we have the mole, since this is stoichiometric reaction, if we talk about stoichiometric reaction, and then we can proportionate. Okay, that's why here we proportionate here to get mass of zinc. Okay, and then we can use the same mole. See, we can use the same mole because in front of zinc is 1 mole. In front of hydrogen is also 1 mole. So by having same mole, of course, zinc is the same mole. But talking about how much X in weight, and then you have to calculate, you have to times with molar mass of zinc. Okay, the difference is weight, but the same is mole. So we can use the same mole because this equation is already stoichiometric. So this term, all this term, you need to remember what does it mean by stoichiometric. Okay, it's actually a relationship between exact amount of reactant react to produce exact amount of product. Okay, when we have this stoichiometric relationship, whatever mole produced, we can start to proportionate. Okay, the difference is we can convert it into what type of weight of the species is. That's it. Okay, another question. 4 grams of solid copper metal react with 10 ml of concentration nitric acid. Imagine that all these sentences were converted into the chemical equation, assuming that this chemical equation is already stoichiometric. I always tell my student, okay, even though this question is from this chemical equation is from this question, always check whether this equation is stoichiometric or not. Okay, even though the question given to us looks like stoichiometric, no, you have to check. Sometimes it's typo error, printed error. Okay, some of my students say, if that's so, this will be free marks. Yeah, free mark. Sometimes you the only one see the problem one, but the rest student have the correct one. So what problem is? You have to complain, but it takes more time lah. That's why even though this chemical equation is given to you, please check it to make sure it is stoichiometric. Okay, so solid copper react with nitric acid, okay, to produce copper nitrate plus NO gas. If you cannot spell out in chemical compound, you just mention NO gas. Normally nitrous oxide gas lah. Okay, nitrogen monoxide and water. Okay, or in terms of stoichiometric amount, we can say that 3 mole of copper react with 8 mole of nitric acid to produce 3 mole of copper nitrate and 2 mole of nitrogen monoxide. Lastly, 4 mole of water form. Okay, so meaning that here we need to interpret it correctly, because after this we will use this to proportionate the data given to us in order to calculate what a question asking us to do. Okay, so 4 grams of copper metal react with 10 ml of concentrated nitric acid. The concentrated nitric acid given here is 12 molar. The 3 products are copper, nitrate, okay, blah blah blah. The NO gas collected and it has volume of 10 ml of STP condition. Okay, this amount is considered as STP condition. Okay, calculate the volume of NO gas should be formed theoretically. Okay, theoretically. Okay, the term theoretically meaning that it asks us to calculate in the stoichiometric. Okay, there are 2 ways of knowing whether it's stoichiometric or in the experimental way. Okay, here the solution asking us to find the limiting reactant is actually we just calculate, as I said earlier, we just calculate data given to us to see what are the information that we get. Here we have the amount and the concentration. Okay, amount and the concentration 0.01 liter 12 molar. Okay, this concentration, okay, 0.01. Okay, the concentration 12 molar, you can get the mole. This is actually the amount of concentrated acid being used. You times these two, you can get the mole. So from this mole, you know how much mole in the chemical reaction here. You see, it's actually being shortened here to proportionate. This is the experimental amount. This is the theoretical amount. Okay, 8 molar is the theoretical. And see, 3 mole, 8 mole, 3 mole is this amount of mole theory. Because we have the equation is the theory. We didn't do any reaction yet. We just given to us the chemical equation, and we know that these all are the theoretical amount of stoichiometric reactant and product. So from the experimental amount, we proportionate it into theoretical amount by comparing with the 8 mole of nitric acid here. Or in other words, we can say that 0.12 mole nitric acid we produce 8 mole. We are comparing between nitric dengan nitric with NO. Okay, NO. So they're asking us NO, the product kan. It's not NO. Okay. So we compare to produce NO. So we are comparing between nitric acid with NO. And this is theoretical amount. It says that 8 mole of nitric acid will produce 2 mole of NO. This is theoretical amount. Here we get 0.12 mole of nitric acid is the experimental amount. Okay. You can put short form like this, or you can put in a proportionate way. If you want to have NO as the product, you put on the right side by having or by comparing reactant with product in the same region. Let's say from the theoretical amount, 8 mole nitric acid produce 2 mole NO. If 0.12 mole nitric acid, it will produce 2/8. See, 2/8 times 0.12 is specific unit. You will cancel, you can get the amount of actual experiment. This is experiment because you need to know from the experiment you produce the experiment. Okay, when you use for copper, you calculate back for copper, you can get this amount. The same calculation, First determine the mole, and then you do comparison by using this stoichiometric reaction. Where these two. Okay, copper ni, but now you are comparing copper with NO. Just now nitric with NO. So we are using copper also. So we calculate the mole of copper. We can know how much NO being produced. Okay. In theoretical, it says that 3 mole of copper will produce 2 mole of nitrogen monoxide. But here, copper that we use is only, we can calculate here. That's why this is the shortened form of operation. You will know the amount of copper being used here. How much more? Okay, experimentally. From here, you start to compare using this stoichiometric, and you can get amount of nitrogen oxide when 4 grams of copper being used. So you can see now, amount of mole nitric acid experimentally being used is only 0.12. It will produce 0.03 NO amount of this. So we calculate based on stoichiometric. Okay, so this NO is also regarded as theoretical amount. Okay, because we didn't do any experimental yet. Same as copper. Given to us is 4 gram. So we try to calculate if we use the 4 gram, how much NO will be produced. So by comparing copper with this product, so we compare this stoichiometric, we theoretically should get 0.04. Okay, so now before saying whether copper or nitric acid is the limiting reactant, we need to see the amount of NO will be produced. Okay, yang akan dihasilkan will be produced. So by having 0.12 nitric acid, it will produce 0.03 NO. By having 4 gram Cu copper, it will produce 0.04. Which is smaller between these two? Of course, NO from nitric acid. Meaning that nitric acid is the limiting reactant. Okay, copper is the excess reactant because it produces more. Okay, it produces more. So we need to give the correct answer because let's say even though we have a lot of copper, okay, we have a lot of copper, but we only have this amount of nitric acid. Okay, so chemical reactant here says that, stoichiometric reaction says that you have to react based on how much nitric acid you have, even though you have stoichiometric. So in other words, in real situation, you have to find which is limiting reactant, because limiting reactant will determine how much product, will determine the real product. Okay, the real product. So that's why we calculate between these two reactants, between the two nitric acid and copper. So we can say that nitric acid is the limiting reactant. So NO here 0.3 molar is the real product. So based on this real product, and then we calculate the volume. Because they're asking us into gas, just calculate into gas volume, you can get the actual volume. Okay. That's why involving limiting reactant, okay, when two reactant is given the value and you were asked to determine the product, first thing first, we have to calculate, we have to determine which one of the two reactant is the limiting reactant. Okay, first. By looking at the product of the two, theoretically, you can see which product is lesser. Okay, the reactant that produces the product is lesser, the reactant is the limiting reactant. Always remember that limiting reactant is the reactant that determine the reaction for the product. Okay, that's why limiting reactant is the main factor to drive the reaction forward. If you have, let's say, 1 kilo copper, 1 kilo copper, but you only have 0.12 mole of nitric acid, it can only react with this amount of copper. Okay, so the important thing is, I say again here, if you were given two amount of reactant and you were asked to calculate either one of the product, first thing first, determine which of the reactant is the limiting reactant to produce the real product. Okay. Another phenomena is using gravimetric analysis. Just now we look at the gas formation reaction. This is one of the example, the usage of solution stoichiometric to calculate the product. This one looks simple. This one looks more complex because it gives to us two amount of reactant. This one only one reactant given to us. Much easier lah. Second one, two reactant were given. Okay. Okay. Another situation, solution stoichiometry also being used in gravimetric analysis. Okay, gravimetric analysis meaning that we react reactant and produce precipitate. Why we produce precipitate? Because we can measure the heavy of the precipitate by weighing the precipitate produced. Okay, of course precipitate will form. We can isolate by drying, and then lastly we determine the mass by precipitate. Okay. One example in this phenomena, let's say 3 gram sample of alloy. Okay. You know alloy? Alloy is combination of 2 or more metal to form a solid new metal, which is plumbum and tin. Some say plumbum ni ada sebut sebagai lead, L-E-A-D. Lead tu bukan lead, lead. Always remember lah. Lalu saya tengok boleh sebenarnya plumbum kalau US dipanggil apa? Dia sebut sebagai lead. Sebab dia tahu L-E-A-D tu lead. Tapi plumbum dia baca tu bukan lead lah, dia jadi lead. Pernah dengar tak dulu unleaded plumbum kan? Unleaded petrol. Zaman-zaman dulu petrol yang kita guna isi minyak tu dia tak filter buang plumbum. Sebab plumbum ni nak filter kena ada proses. That's why scientists let it be in the petrol, guna aja. And then banyak penyakit, scientists start remove plumbum by having another chemical replaced with plumbum. Sebab tu at that time unleaded petrol murah. Unleaded petrol mahal. Kau nak kena buang plumbum tu. Lead, bukan lead lah. Unleaded. US buat tin, bukan tin biskut tu. Of course lah tin biskut, sebab tin biskut tu semua sadu dengan sternum. Sebab tu gambarnya dia pun panggil tin kan. Sebenarnya bukan tin, sternum. Tapi US panggil tin until now. Okay, so back to this question. 3 gram sample alloy which consists of plumbum and sternum was dissolved in nitric acid. And then sulfuric acid was added to this solution, which precipitate 2.93 gram of plumbum sulfate. Tak usah kisahlah, tiba-tiba ada nitric acid and then ada sulfuric acid. Doesn't matter. What we're looking for is the precipitate. Dia nak guna 3 jenis acid ke, whatever it is, doesn't matter. Okay, and then dia kata, this sulfuric acid was added to the solution, which precipitated 2.93 gram of plumbum sulfate. Assuming that all the lead was precipitated, assumption is also important because we need to assume this because we need to have the correct stoichiometric chemical reaction. Let's say if you did assume this, maybe another type of product or byproduct produced, so it will deter or it will ganggu lah. We will ganggu ataupun kita kata we need to have chemical reaction yang stoichiometric. Okay, that's why by assuming this, so another product we cancel. So we much easier to correct this chemical reaction to become stoichiometric and also plumbum, because we cannot remember this. Sometimes we give one piece of paper, periodic table, all of the element, not the compound. So sometimes compound you need to calculate. Once you give a wrong compound equation, of course you calculating the wrong molecular weight of the compound. So bear in mind. So this is a chemical equation given to us. Again, I said just now, please check the stoichiometric of the equation, meaning that the mole reaction react between the reactant and the product are the same. Okay. In other words, in chemistry they use the term equivalent. Itulah English ni dia lebih more lebih tepat, sama tapi tak setara. Setara kan, equivalent setara kan. Melayu selalu sebut sama tapi tak serupa kan. So in chemistry they put higher level of same, they use the term equivalent, equivalent mole. Plumber is 1 mole, is 1 mole. This is ion, doesn't to do with mole. Okay, this is ion. Okay, charged ion. Sulfate, 1 unit sulfate. So sulfate. Okay, so with the data given to us, calculate first what do we have. Okay, weight of plumbum sulfate produced. Okay, the precipitate. So divide with the molecular weight of plumbum sulfate, we can get mole of plumbum sulfate here. This equation under this example almost the same as the first example here, the simple one kan. Second one, the more complicated. See, same as this one. Only one given to us, much easier lah. Once we get the mole of the reactant, automatically we can calculate whatever need given us to calculate. Then 1 mole palm sulfate contain 1 mole palm. Or we can interpret like this. Let's say here lah, because the same mole, so much easier lah. 1 mole of palm sulfate produce 1 mole palm ion, 1 mole sulfate ion. Or if we calculate in the real situation, okay, given to us, produce 2.93 gram, which is equivalent to 0.00966 mole of plumbum sulfate, we can interpret this as, if this amount of plumbum sulfate being used, we also produce 0.00966 mole of plumbum ion and also 0.966 mole of sulfate ion. Okay, so it's become much easier to calculate the percentage. Okay, percentage of stannum. Okay, get the amount of stannum. Okay, stannum here is also 1 mole. Get the amount of stannum. Okay, and then here, okay, stannum is not given here, plumbum only. Plumbum, 12 gram plumbum. Okay. Okay, because of total gram sample, 3 gram. Okay, we just minus total minus gram plumbum, you will can get the stannum. So amount of stannum divided by the total weight of sample, you can get the percent of stannum. This much straightforward problem. Okay. Another one. See, just now we have only one reactant. Just now, now we only have 2 reactant with 1 product. Of course, we are targeting the product because the product will be precipitated out. So they measure the product. Okay. Let's say this question. 2 gram sample of limestone was dissolved in hydrochloric acid and all the calcium present in the sample was converted into calcium ion. Okay. Excess ammonium oxalate solution, okay, NH4 C2O4 was added to solution to precipitate the calcium ion as calcium oxalate. Yeah, calcium oxalate, CaC2O4. Okay, the precipitate was filtered, dried, and weighed to a constant mass of 2.45 gram of this calcium oxalate. And the question is, determine the percentage by mass of calcium in a limestone sample. This actually, there's another question here, but it's not appear here, which is the reaction of sample limestone with hydrochloric acid. Okay, this reaction will produce calcium ion. So product of calcium ion, and then this is the second equation shown here. Okay, product of calcium ion produced by reacting the limestone with hydrochloric acid. So this calcium will be reacted with oxalate, ammonium oxalate. So they will produce calcium. This reaction is actually asking us to know how much calcium in the limestone actually, because calcium in the limestone need to dissolve the limestone first, so we can separate calcium with the rest of the ion in the limestone. Maybe some of them impurities. Okay, to get more pure calcium, dissolve first with hydrochloric acid. Okay, so calcium become single ion, and then capture this single calcium with another type of chemical. We need to study what type of chemical that's suitable to capture the calcium, and finally, this capture will produce a good precipitate. Okay, in gravimetric analysis, we need to know the characteristic of good precipitate, which is they have good high molecular weight, good molecular weight, and also have, of course, have high weight because of the molecular weight is bigger. Why? Because we are using gravimetric, so we need to measure by weight. If we produce very less weight, how are we going to measure? Okay, that's why the accuracy of the gravimetric is to have a good product of precipitate. Okay, that's why the selection of good chemical in order to capture our unknown is very, very crucial. In this case, they are using ammonium oxalate. See, very, very long equation, and you can total up the mass, how much? So big. So of course, when they capture calcium, they also produce calcium oxalate, quite big. But after that, even though you have the total mass of calcium oxalate, all you have to do is you just compare mole ratio between the calcium and the whole ion, and then you can get the percentage of calcium. Okay, that's the story behind of the reaction. Okay, go back to the equation. Yeah. Okay. We already have the calcium oxalate. Okay. We want to see the mole fraction between the ion. So calcium combined with oxalate, we produce calcium oxalate. Okay. So it clearly shown to us that 1 more calcium, 1 more oxalate ion, 1 more calcium oxalate. Okay. So calculate what given to us first. Okay. Mole of calcium oxalate precipitated. Okay, 2.45 gram here. Okay, with the molar mass of calcium oxalate not given, so you have to calculate lah. Calcium oxalate, how much? To 128.1. Get the mole. This is the mole. Okay, the experimental mole of calcium oxalate being produced. Okay, calcium oxalate being produced. Therefore, dia kata 0.0193 calcium ion is reacted. Okay, because all the same mole. Okay, because we are comparing the same proportionate number amount of mole on each reactant end product. So much easier for us to get the mole of calcium. See, same mole calcium is mole of oxalate. We are comparing the same amount. So we can convert back to weight of calcium, 40.1 gram molar mass of calcium per mole. We can get 0.60 gram of calcium actually in the limestone. So percent by mass of calcium in sample. Always remember sample, not per. Some of student we per this with 2.45 gram. This common mistake done by students. Normally they will per with 2.45. Of course, this calcium finally precipitated out in this form of calcium oxalate. But the question asking us, in the limestone sample, okay, determine percentage by mass calcium in the limestone sample. You're not asking us calcium in the calcium oxalate. Nak confuse students or not di sini kan? Kalau dia kata determine the percentage by mass calcium in the calcium oxalate sample, adalah student akan calculate per dengan 2 gram sampel. Apa? Soalan pun straightforward kan? So, hati-hati. Apa-apa pun hati-hati. Okay? So, in conclusion, percent mass by mass of calcium in sample of course referring to limestone. So, per 2 gram of limestone, you can get 38.3% of calcium in the limestone. Okay, third phenomena, the use of solution stoichiometric is the acid-base titration. Actually, we can react acid and base without using the titration. Okay, but we need to measure accurately by using measuring cylinder, but it's quite difficult. Okay, so most of the scientists use titration to react in a stoichiometric amount of acid and base in order to neutralize the reaction. Example here, calculate the volume of 0.6 molar sodium hydroxide solution needed to neutralize. Okay, when talking about acid and base, of course, the reaction will produce neutral solution. 20 ml of 2.45 sulfuric acid solution. Okay, always remember, always bear in mind, in any situation, okay, gas, solution, gravimetric, acid-base phenomena, when talk about stoichiometric, okay, you need to have chemical reaction in stoichiometric form. Okay, and then you can calculate whatever asking us to calculate. Okay, always bear in mind. Okay, of course, this here much easier because you were given already the chemical equation with the stoichiometric amount. Okay, I said just now, please bear in mind, always check first before you do operation on the calculation. Okay, to cut short of this, okay, 2 amount of sodium oxide, we have 1 mole of sulfuric acid to produce 1 mole of sodium thiosulfate with 2 mole of water. When the compound contains sulfur, normally we pronounce as thio. Okay, we didn't pronounce sodium. Shape is very useful. Okay, because we have 2 entity of reactant. You can use A, B, or A, B here, or A, B here, any of this reactant or product, doesn't matter. If you choose this one, these two, you have this one, these two. Okay, MAB, BBB. This is the general term, okay? Because we are comparing the mole. So M times B is mole. Mole of what? Mole of A. Okay? If A is sodium hydroxide, it becomes 2. Yeah. If B is sulfuric acid, it becomes 1. Okay? Now it's referring to between sodium hydroxide and sulfuric acid. Doesn't concern with product. Okay? Doesn't concern with product because this is titration. Titration only concern on the reactant between the 2 reactants. Gravimetric only concern on the product. Okay? So, put all the data given to you. Make sure this referring to the stoichiometric reaction. A is referring to sulfuric acid. Okay, 2.45 molar volume of sulfuric acid. And the rest, and you rearrange, you can get volume of B. B is referring to the sodium hydroxide. Sodium hydroxide, which one? Okay. Calculate volume of sodium hydroxide needed. So this one. Okay. Another question. Calculate the mass of sodium hydroxide required to neutralize 57 ml of 0.5 molar sulfuric acid. Now the equation is not given to you. Okay. But the equation much simpler. Okay. Calculate the mass. Just now asking you to calculate the volume. Now you were asked to calculate the mass. Okay. So this is the equation. So calculate first information given to us. Mil, concentration, you can get mole. Always remember this is sulfuric acid. This is molecular weight of sulfuric acid, 57 mil. Mole per liter. Okay. 57, 0.5. Okay, just get mole first. Okay. Sorry, yes, you get mole first. From this volume and concentration, you can get mole first. Then 1 mole sulfuric acid react with 2 mole sodium hydroxide. This statement is taken from the stoichiometric. Okay, 1 mole sulfuric acid, see, react with 2 mole sodium hydroxide. So if 0.015 mole of sulfuric acid, so it will react with, this already simplified for you. It's actually 2/1 times 0.0185. It produces 0.03 sodium hydroxide. So your question asking us to convert into mass. Okay. So you just time the molar mass of the sodium hydroxide, you can get 1.48 gram. Anyone knows what type of physical of sodium hydroxide when you use to produce or to dissolve into solution? Does anyone know? What is a physical characteristic of sodium hydroxide? Does anyone know? What is the form of sodium hydroxide?
Aqueous.
Sorry? Aqueous.
Solid.
Solid. Yes. But sodium hydroxide, in terms of the shape of sodium hydroxide, is pellet. You know pellet. You know tablet. Panadol is shape of cylinder, tablet. Sodium hydroxide in form of pellet. Sodium hydroxide is very, very hygroscopic, meaning that you need to prepare much faster after you weigh certain amount of sodium hydroxide, because it will absorb moisture from surroundings. You should measure only sodium hydroxide. If you do the measuring very, very slow, sodium hydroxide will automatically absorb moisture from the surrounding. That's why sodium hydroxide is very, very hygroscopic. So you need to prepare much faster when you dealing with sodium hydroxide. Okay. Last part, which is redox titration. There are 4 events when solution stoichiometric being used. Okay, the last part is redox titration. Okay, redox titration, same like the acid-base titration, but redox titration involve oxidation and reduction in the one reaction simultaneously. So either the titrant is the oxidation, or at the bottom is reduction, either or. You just titrate. Okay. Eventually, the reaction will stop. Why? Because you reach the equivalent point. This is the equivalent point. When you do titration, of course, amount of reactant react to produce product in the same amount. It's equivalent amount. So reaction will stop. But actually in titration, we cannot find equivalent point, because our naked eyes, we cannot see the equivalent point, because during titration, we can see only the reaction stop or the reaction completed by the help of indicator. You know indicator? Penunjuk kan? Acid-base titration. How do we know that the acid and base completed reacted between the two without having the indicator? If you didn't put indicator, you titrate sulfuric acid and sodium hydroxide. You use 1 gallon of sodium hydroxide, but you cannot see the completion of the reaction. That's why in redox titration or acid-base titration, you need to have indicator. You put 1 or 2 drop of indicator, okay, to help you to see the reaction is completed. However, when you use indicator, that reaction is completed, you are actually excess amount of titration being put into the both reaction to complete the reaction. So you are excess amount of titration. In other words, you already exceeded equivalent point. Okay, but in calculation, the exceedance of equivalent point in titration is regardless a very, very small amount. It's about half drop. I think half drop. It's very hard to get half drop. 1 drop. Normally people use 1 drop. So when you put 1 drop, okay, you can see you start from the beginning titration. Can you imagine you titrating acid and base? You put indicator, you start titrate, and then you see once the acid or base touching the surface, the color appear, and you start shaking, the color dissolve. Okay, to a certain extent, last drop or maybe a few drops, you can see the color start to become permanent. Okay, and then you start slowly. Okay, start slowly swirl. And when you put last drop, you can see that the permanent color, the color produced become permanent. Okay, that's why it's considered we call as endpoint. Okay, so in titration there are there are 3 situations. Okay, endpoint, equivalent point, initial point, we didn't say that initial point. Okay, equivalent point and end point. You cannot see the equivalent point, but theoretically here said that equivalent point is actually amount of reactant completely react with exact amount of mole of reactant to produce product. Okay, equivalent point. As I said just now, you cannot see reaction without the help of indicator. So if you put indicator, you are actually exceeded equivalent point, just to help you to stop the reaction, just to say that the reaction is already equivalent. But if you want to calculate the actual one, you don't have to do titration actually. You can calculate secara theoretical. Okay, just to give an idea what is all redox all about. Okay. Okay. The equivalent point is reached when reducing agent is completely, see, they use the term completely oxidized with the oxidizing agent. If you are referring to acid-base titration, we can use the term here that the equivalent point is reached when acid is completely, okay, react with the base. Apa tak the difference between acid-base dengan redox titration? So it's the same because they are using the same equivalence point. Okay. So here there are two common oxidizing agent. Agent pengoxidaan kan, oxidizing agent, manganese ion. How do we know that manganese have 7+? 7+ here. We need to calculate the oxidizing state of the manganese. Manganese plus 4 times -2 equivalent to -1 over the whole ion. So -8, 4 times -2 is -8. You bring forward after the equivalent, minus with 1, minus, we get 7+. So here, manganese for oxidant here, oxidation state here is 7+. Okay, very, very strong oxidizing agent. Okay, here, because it's single, we look at the ion. So here, oxidizing state of manganese is 2+. Sorry, +2. 2+ is ion. +2 is oxidation state. Terbalik sikit kan? 2+, +2. Hati-hati. That's why chemistry is very, very important. Okay? How you write, which one first. Sometimes I'm asking my student to write M and with a proper writing. Most of the students will write M with bigger M, but still not a capital letter of M. You know what I mean? M kan? Dia tulis M besar, tapi M tu macam huruf kecil. So kadang-kadang saja nak gurang student, especially during quiz, even though the question is right, I give wrong answer to the student, and most of the students start pening. Why, sir? I don't know, kata. Are you properly written your equation? Okay. M besar dengan M kecil. Besar mana tu M you tulis, dia tetap huruf kecil. Faham tak? Kan? So chemistry is very, very critical. You put 2+ or +2 is very, very important because you need to differentiate between ion and oxidizing state. Here is +7. Here is +2. Okay. For dichromate ion, okay, +6 here. Here is +3. Reduced to 3. Okay, reduced to 3. Meaning that in order for this dichromate to turn into +3, it already received another 3 electrons. Only electron can be transferred. Give and take. Only electron. In a nucleus atom, proton, neutron only reside in the nucleus. The electron only the outside of the nucleus. So in any reaction, only the outer electron will involve. So meaning that one species will receive, another species will donate. Okay, this only two. There's no other than two. Receive and donate. Okay, so in this state, 7 plus 7 become +2, meaning that this manganese in the purple condition already received 5 electron to reduce to +2 state. Here, chromium receive 3 electron to go to green color, which is chromium 3 state. Okay. Okay, one example, as usual, given to us. Okay. Okay, this equation were already break up just to show to us the ion state. It doesn't matter as long as it's same, referring the same amount of mole reacting in the chemical reaction, as long as when we check the reactant mole with the product mole are the same. We are not talking about the ion, P plus here, 2 plus here, but we are talking in front of the formula. 5 here, yes, 5 here. 4 for the whole water, yes. If you can get for the whole water, you just 4 times 2 for hydrogen, 8. So you have 8. Okay. 4 oxygen, 4 for oxygen. Okay. I think most of students will familiar all these things. Okay, let us look at the question. 60 ml of 0.13 molar calcium permanganate or potassium permanganate to oxidize 25 ml of ferrous sulfate. If this is, you can check whether this is F2 or F3. Normally this is F2 once you calculate the oxidizing state. If you know this is ferrous Fe plus 2 for the oxidizing state, you need to properly pronounce it as ferrous sulfate. You cannot sebut sebagai ferric sulfate. Nanti orang tahu yang kita tak tahu. Kata dah belajar kan, tapi tak tahu. Bahaya tu kalau orang tahu kita tak tahu. Kan? So jangan tunjuk orang kita tak tahu. Kata terror kan, sebut ferric sulfate. Orang kata kita tak tahu sangat. So in this case, you have to calculate. If you're uncertain, you calculate. Oh, F here is plus 2. Meaning that F ini adalah ferrous sulfate. For 2 plus, normally we pronounce as ferrous. For Fe3 plus, we pronounce as ferric. So, dia kata calculate the concentration of ferrous sulfate solution in molarity. Kira kepekatan ferrous sulfate. Okay, molarity. And another question, jangan lupa, most of the second question is put at the end. Normally student, we only focus on the first inside the situation. From this one, I think better put number 1, need to calculate 1, concentration of ferrous sulfate. 2, net ionic equation. Right first. Once you completed, you tick. This is example. So, calculate first what do we have from the information. Okay, this is general information of mole, regardless of reactant or product. Okay, as I said earlier, you can proportionate between reactant and reactant, product and product, or reactant and product. You can proportionate within the chemical compound or interchemical compound. Okay, you just have to have the mole between the comparison. MAV, okay, MBVB. Okay, so put all the information provided to you. You can get molarity of the solution. Okay. Okay, check quantity 2. Normally check quantity 2 student need to do. Okay, question 1. Okay, I did 5, meaning that iodine at the stage of +5 oxidation state. Okay, I did 5 ions react with acidified iodide. Ion as shown below. Okay, here the equation given to you. Iodide normally comes from potassium iodide. So here it only shows the counter ion because potassium doesn't react. What react is the counterpart of it, which is iodide. Okay, iodide ion, this iodide, because this is equivalent to produce iodide with iodide. It's not easy to produce calcium iodide or iodide. You need to mix between these two and then you can get that certain amount that you calculate. So here it says that iodide 5 react with acidified iodide Okay, you need to have acid to produce iodine. So iodine is not easily to produce. Okay, you have to create a solution, iodide with calcium iodide plus acid, and then you have iodine. Okay, iodine produced here, see, okay, the iodine release, meaning that the iodine produced here is then reacted with thiosulfate. This is thiosulfate. Just mentioned just now, it's not thiosulfate. Sorry, sulfate. Sorry. This one, yes, this is thiosulfate. Okay, so once this iodine produced, it will be titrated with thiosulfate. Amount of the produce will be titrated with thiosulfate to produce iodide and S4O6. So, question is 16 ml of 0.2 iodide here. Iodide reacted with excess acidified iodide ion. Okay, iodide ion. If all the iodide liberated reacted with X of 0.4 molar of thiosulfate ion, calculate the value of X. Where the X is? Excess acidified iodide ion. If all the iodide reacted with X of thiosulfate ion, calculate the value of X. X here is referring to the excess amount of iodide. Excess amount of iodide. Excess. Okay. Okay. So iodide form, okay, use is 0.01 by having this information. Yeah. Okay, convert into liter, you will get 0.012 mole. Okay, mole of iodine liberated. Liberated meaning that excess. Being used in here, 1 mole iodide is 3 mole iodine. 1 mole iodide is 3 mole iodine. The exact amount. Okay, exact amount. It asks us here is to calculate the excess amount of iodine. But here, it produced liberated, any liberated iodine will be titrated with thiosulfate. So any excess will be calculated. Okay, mole of iodine liberated, 1 mole of iodine produces 3 mole of iodine. So if this amount of iodine, okay, iodine is actually only this amount of iodine. Okay, so this amount of iodine. So how much thiosulfate needed to be titrated? Okay, how much thiosulfate needed to be titrated? See, so 1 mole iodine will react with 2 mole thiosulfate. Okay, this one. So if 0.0360 mole iodine, it will use or it will consume a titration of 0.02 thiosulfate. Okay, X here is actually the thiosulfate used to react with the excess of iodine. The X is the thiosulfate. Okay, with the thiosulfate. So volume of thiosulfate is convert back more into concentration given. You can get the milliliter of thiosulfate. Okay, 180 milliliter is quite a lot now. Normally in titration, normally it's not as much as 50 ml, not more than 50 ml. This is some calculation example. Okay, some example. So we completed subchapter 110 and 1.9. Okay, nak stop sekejap.
Okay, maybe we can take 5, Prof.
Yeah. Silakan.
Okay, students, so we can take 5 minutes break before we continue with our second topic 2, subtopic 2.1. So we give a break. 5 minutes. Okay.
Asasi kan setahun dah dia punya tempoh kan?
setahun 2 sem je.
2 sem je.
Ha.
Maknanya kalau siapa ambil tingkatan 6 kesian lah.
Ya, setahun setengah.
Oh, 1.5.
Kalau tak silap saya lah, form 6 setahun setengah Prof?
Saya tak pasti. Dulu ada sebutkan 6 bawah 6 atas, maknanya 2 tahun lah. Sekarang pula.
Saya tak sure tapi macam pernah dengar setahun setengah je sekarang dah.
Kena kurang sikit lah. Masih advantage matrik dengan asasi lah. Because they only 1 year.
Betul. Tapi kalau tak silap saya lah, matrik pun ada program 2 tahun.
Oh. Matrik ya. Depend on program kot.
Betul.
So dia pergi ke degree tu. Tapi itulah. Kalau setahun saya pun tak boleh nak imagine how compressed. Dulu kami 2 tahun 4 semester.
Untuk asasi, untuk matrik dulu.
Lama. Tahun bila saya dulu 88. Lama lah. 4 semester.
4 semester.
Bayangkan.
Tapi silibus makin besar lah kan silibusnya, coverage dia. Sebab macam student asasi ni dia 14 minggu je satu semester. So macam compact, betul-betul compact lah.
Betul.
Tak sampai setahun pun kiranya kalau 14 dengan sem 1 sem 2.
Macam asasi UiTM, contoh macam asasi UiTM ni, after completed asasi ni, not necessarily UiTM akan ambil kan?
No, they have to go through to the UPU lagi.
Oh, UPU lagi lah. Sebenarnya lepas tu still option given by UPU lah.
Betul.
Maknanya kalau dia buat option katakan UiTM tak semestinya dapat.
Tak semestinya, based pada result jugalah nanti.
Oh.
Requirement university tu.
Kami dulu lain. Kalau kata asasi pendata by UM, so dia feeder for UM.
Betul.
Kalau kawan-kawan mana yang matrik di UKM, dia feeder for UKM.
Betul.
Oh, sekarang ni dah.
Tak, dia open balik kepada UPU. So student ada option lah kiranya.
Oh, pelik juga lah.
Sayang lah kan sebab tak jadi feeder kepada UiTM sendiri balik kan.
Sebab tak tahulah, kadang-kadang susah juga nak cakap. Sebab yelah tenaga pengajar kita semua UiTM kan. Suddenly kadang-kadang yelah bukan apa. Kadang-kadang universiti lain dia akan kata, oh ni asasi hasil kita, hasilan daripada UiTM tak ni lah, itulah sebagainya lah. Kadang-kadang benda-benda tu dengar kan. Because asasi not only UiTM yang akan conduct kan.
Betul.
Dia jadi macam tak tahulah, kalau itu bukan isu di KPT mungkin tak ada masalah lah kot. Tapi yang saya tahu semua asasi sekarang ni semua top student ni.
Requirement dia tinggi jugalah untuk masuk kan.
And then program yang dia minta untuk next pula very high pula dia punya CGPA-nya.
Betul.
Ada yang our student dulu dia sanggup opt for diploma science. Bila kami tanya pasal apa, result very good SPM. Pasal apa yang ambil diploma science? Dia kata dia dah macam fokus lah. Dia tanya orang ke saya tak pasti. Dia kata susah saya nak compete, saya kena maintain at least 4 flat. Dia kata, oh ya ke, saya tak tahu pun. Dia kata dia ada ikut jejak langkah senior dia because dia aim for medic kan. So memang pro lah after dia memang every sem
Dinis
pendidikan tu. So dia dapat 3.8 ke 3.75 and dia buat medik di Unimas. Maknanya boleh lah.
Cuma jauh sikit lah kot perjalanan dia.
3 tahun. Tapi
sebab
dia kata study tak stres. Memanglah dia boleh skor.
Betul.
Tapi
Sebab 3 tahun compare dengan setahun kat asasi kan.
Tapi diploma sains 2 tahun setengah. Sorry 2 tahun.
2 tahun setengah. Okey. Tapi nanti kalau dia masuk diploma dia boleh pindah kredit juga kan apa yang dia dah belajar.
Boleh banyak. Dia untuk diploma dia akan lompat selalunya tahun 2 lah.
Oh.
Tapi kalau medik I'm not sure. Kalau medik sebab dia ada subjek yang macam common macam chemistry. Kalau dia pernah ambil chemistry, kalau good grades dia boleh lah exempted. Tidak, dia tak boleh juga, kena ambil balik. Macam diploma sains dia tak ajar biochemistry dan mendalam. Kalau kerana macam perubatan kan dia nak dalam kan.
Betul,
Mungkin
betul.
tak banyak lah paper yang dia exempted. Tapi dia pun sanggup. Dia kata daripada tak dapat langsung.
Betul sebab saya rasa macam ada kota masing-masing kan.
Betul.
Uh,
Ada nak tanya Nurul Izzah? Ya.
Nurul Izzah.
Ya, Nurul Izzah.
Nurul Izzah.
Dia tertekan.
Untuk topik 2.1 ni ringkas je rasanya Prof kan? Sikit je cover.
Buat sikit je. Dapat overview lah sikit. Saya pun tak prepare slide saya sendiri dah. Mula saya dengar nak prepare slide sendiri.
Dah tak sihat hari tu kan demamnya.
Lepas tu bila tengok malam tak sempat ni kata. Lepas tu saya buka slide tengok dah ada dah. Cumanya it's good to have yang orang punya, tapi saya tak boleh nak familiar dengan orang punya.
Betul.
Kebiasaannya macam tu.
Betul.
Sebab tu macam UiTM saya nampak ada kelemahannya because for each subject dia ajar oleh seorang saja lecturer. Because we shortage of lecturer sebenarnya, betul lah kan. Tapi our neighboring university kat sini, UniMap, each subject will be teach by 2%.
Oh, okay.
Mesti, yang tu mesti. Sebab dia kata macam syndicate marking apa semua kan. And then bila kami discuss, dia kata every sem kan course lecturer, they have to go for conference kan. Jadi betul lah, half semester kau aja dulu. Jadi dia boleh manage time lah. Betul. Dia kata kadang-kadang salah seorang demam ke, emergency ke.
Ada backup lah.
Lepas tu saya lawak, saya kata tak apalah. Maknanya universiti hampa ni lebih lecturer lah. Same amount of student dengan kita. For example, kita di cawangan Perlis ni kita ada lebihkan 7,000 lebih student. They also have 7,000 lebih student. Tapi dia full-fledged university. Tapi daripada bilangan syarah apa? Double of us.
So loading luar rendah lah.
And then another thing is they limit the number of student per class. Memang dia ada bawah badan profesional lah, because most of the technical engineering apa semua dia limit to 35 students. Kita even teknologi pun kalau tiba-tiba di semester 30, next jadi 120, even kita pernah touch 180 per semester. Maknanya yelah the quality of lecture tu reduce lah kan. Takkan sama lah. Benda tu yang jadi masalah. Banyak faktor lah. Tapi try to, pernah dah kita propose, tapi susah lah until now. Bukan kata nak dapat lecture tambahan, lecture yang sedia ada pun tak cukup.
Kekangan kat situ lah, kekangan.
Macam mana kan, kita terpaksa guna apa yang kita boleh guna lah kan.
Betul.
Okey kot semua. Makin cepat. Dapat Izzah di asasi lama mana dah?
Daripada 2011.
Lama juga lah.
Daripada Puncak Alam.
Daripada FSG bukan?
Bukan, tak sempat FSG. FSG sebelum 2008 kot kata saya. Lepas tu orang transfer ke Puncak Alam, lepas tu transfer ke Dengkil.
Dulu sebab saya join 95 lagi, ada perpecahan antara FSG. To those yang background engineering, dia akan go for engineering lah. First degree engineering kan. So yang mana bukan engineering, teknologi semua bawah FSG lah. Even FPA, pertanian break up from FSG juga.
Agrotech tu.
Ya, kalau tengok first degree more towards tanian engineering tanian semua, dia akan shift to FPA lah. Banyak pecah lah, dah jadi FSG alone. Atau FSG pecah pula pergi asasi.
Tapi nanti student balik-balik ke FSG juga kan kalau dia sambung degree.
Degree, yes, betul. Macam okay kot.
Okay, student, can we continue with our second topic?
Yes.
Okay.
Yes.
Okay, Prof.
I need to project new slide.
Yeah, the slide.
Okay, wait. Show. Okay. Is it okay? The slide?
There's no slide, Prof.
Oh, belum lagi.
Tak ada.
Tapi dia tulis stop presenting.
Saya rasa Prof kena buka yang daripada slide PowerPoint tu.
Dah buka. Dah nampak? Okay.
Tak ada.
Belum.
Sekejap. Window. Okay kah? Is it okay?
Tak nampak, Prof.
Baik. Dia tulis you are presenting to anyone. Tak nampak ah?
Tak.
Tak.
Dah buka kan? Sekejap.
Prof present the whole screen ke entire screen Prof? Kalau entire screen memang kena buka daripada slide tu, unless kalau Prof buka a window ataupun a tab. Memang kita boleh select lah nanti mana satu yang dia akan preview.
Sekejap lah. Kalau kat window kan window lain kan?
Tak. Window nanti kita boleh select. Window, window saya rasa daripada boleh select mana yang Prof nak view kan. Window tu. PowerPoint yang mana satu.
Okay, yang ni?
Okay, nampak dah.
Okay ya? Oh, tadi di belah kiri. Okay, sorry.
Okay.
Alright. Okay, so our last part under the topic of 2.0. We will look into the electronic structure of atom, little bit on electronic structure of atom, periodic table and periodicity. Maybe not all because this is just an introduction. Okay. So we will cover a few for today, the Bose model of hydrogen atom. The purpose of this topic is to state the postulate of the Bohr atomic model of hydrogen and state the weaknesses in Bohr atomic model. Okay. Actually, before Bohr model of hydrogen atom being introduced, the electronic structure of atom, electronic structure meaning that the electron configuration outside the atom being stipulated by certain scientists. Started with J.J. Thomson, followed by Niels Bohr, next by the Sommerfeld, followed by Rutherford, and finally Erwin Schrödinger. Okay, now we just look at the Bohr's model. Okay, Actually, Bohr's model is they propose the planetary model with the theory that electrons revolve around nucleus. Okay. Bohr developed a hydrogen atom, explaining how the structure of the atom changes when it undergoes energy transition. And then another statement from him, a major idea is the energy of the atom was quantized, definite amount. Quantized meaning that this definite amount of energy, okay, and amount of this energy is related to its electron's position. In last statement from him, Bohr suggested that electrons could only orbit, okay, move in a certain size surrounding the nucleus, okay, in a specific orbit or shells. They call as shell with a fixed radius. This is the idea from Niels Bohr, talking about nucleus surrounding the electrons surrounding the nucleus. Okay, because electron they have specific energy when they surrounding the nucleus. Okay, and this energy they use the term quantized. Okay, and this energy can be transient. Okay, transition. Okay, experiment done by Niels Bohr. Okay, he did when electric current is passed through a glass tube. Okay, glass tube. This gas discharge contains hydrogen gas. So he applied electric to produce a film of we call blue light. They put slit, okay, to have very tiny light from the hydrogen, and then pass through the prism. Okay, the light is passed through a prism and split into 4 narrow bands of bright light, 4 different colors, and each color it has its own wavelength. You can see here from violet, blue green up to red, different wavelength, and the different wavelength, of course, representing different energy produced by this light being separated. Okay, actually hydrogen has 2 electrons, only 1 electron, but with different transition of energy due to different colors that produce, because the electron receive energy from the discharged electric to produce different energy by its color. So he described to us that an electron absorbs energy in the form of photons. He used the term photons, okay, meaning that energy being absorbed by the electron can be measured. The amount of energy supplied to the electron can be measured. They use the term photon. Okay, most of the scientists at that time are from physics. That's why they use the term physics. This is a physicist. Okay, the electron absorbs energy in the forms of photons to get excited. Okay. This is the energy level. Okay, once energy being supplied, okay, energy being supplied, the electron will absorb the energy. Certain amount of energy being absorbed, they calculate as a photon, and then if certain energy just enough to kick the electron out of the first level to the next level, they call as next orbit. Okay, calls as excited state. Okay, excited state. Keadaan teruja lah, kan? Macam bahasa Melayu pun sudut baratnya. Okay, electron when it absorb energy, so excited, extra energy, it will transfer to a higher energy level. Okay, to get to this level, you need to have certain energy. Macam kita panjat kan, kita nak ada sebenarnya kita kena ada certain energy. Nak naik lagi, kena ada energy lagi. So this amount of energy is measured. Scientists measured and they call as photon. Okay, to a higher energy as long as the photon's energy was equal to the energy difference between the initial and final energy level. So in order to have from 2 to 3, there is specific amount of energy, and the difference between 2, okay, itulah yang membolehkan between the energy to level move the electron from lower state to higher level states. The excited electron would be in a less stable position, so it would quickly emit a photon to relax back to a lower, more stable energy state level, which is called as ground state. Okay. Always bear in mind, once the energy being transmitted to higher level, this level is not considered a ground level, because once receive a photon of electron, a photon of energy, it stays at unstable state. Okay, unstable state, and eventually it go back to the initial state. But going to the energy state level, the initial one, it will produce its own photon. And this photon, same amount being produced with the same amount absorb the electron. Absorb back to have another level of energy, because this transition state, ground state, by release back the energy. Okay, to remember, which is photon, which is energy being absorbed by the electron state, and also the excited state. Okay, in this position, also referring back to the ground state, which is the stable state. And each state in S is level by referring to the wavelength. Okay, that's why equation of energy, E is equivalent H over H time mu, mu, flying times velocity. So each of these is nanometer wavelength. Okay. As can be seen here, ground state is always back to 2, and is equal to 2. Okay, back to ground state. As portrayed in this photo, you can see different colors being depicted just to show the different energy level of each excited state. Okay, starting with 3, 4, 5, 6, etc. Okay, as depicted in this photo, also you can see from the initial state excited to next level. Okay, because this is a transition state, we will go back to the ground state, and photon will be emitted. And this emitted photon has been captured by the gauge on this experiment by having this film to show that this actual electron being excited to a certain level. Okay, regarding Bohr's model of hydrogen atom, so Bohr only explained hydrogen atom. Of course, simple, hydrogen atom only has one electron. Kan? Senanglah nak cakap kan, one electron. So even though Bohr's model is very, very important, it's a starting point of explaining how electron is being distributed around the nucleus. So he postulate ni macam dia give pemerhatian lah based on his experiment. It's not kemungkinan macam teka-teka tak. Postulate ni strong more than pada probability. Probability maybe, but postulate ni is based on his observation on a specific running curve of experiment. So it's true because it's referring to hydrogen atom. Okay, so let us look at the postulate from Bohr's model. Okay, the hydrogen atom has only certain energy level. Yes, the electron in hydrogen atom revolve around the nucleus in a fixed circular orbit. Okay, a fixed circular orbit. Let's say this is the first orbit. This one orbit. Ingat nak cerita kartun dulu kan, macam ada orbit kan. So this electron orbiting the nucleus. Depends. If the atom has only one electron, it only has one orbit, continuously orbiting the nucleus. If the element have more than one electron, you can imagine how many orbits surrounding the nucleus without any one of the electron colliding each other. Can you imagine that? Itu baru level atom kan, belum level apa ni galaksi sana lagi tu. Until now tak berlanggar satu pun. So dia kata the atom has only certain energy level. This what being postulated by Bohr. Dia kata memang atom hanya ada satu energy level because hydrogen only have one electron, and this electron revolve surrounding the electron in circular orbit. Okay, up to now other scientists dia tak tolak this postulate. It's true only for hydrogen atom. Okay, and then it's called this energy level is quantized. Quantized meaning that this energy is a specific amount for the electron to stay surrounding the nucleus at that orbit, which is certain amount of energy. Pernah dengar cerita kan yang ISS, ingat tak ISS kan, international apa ni, yang mengelilingi stesen yang mengelilingi bumi tu. Dia punya station tu besar tak besar macam bandaraya. Can you imagine dia boleh stay at that orbit? Because energy at that level, scientists already calculated to stay at that level from being tarik oleh gravity ke bumi dalam keadaan yang very very strong to stay at that level. So they have to have that energy to surrounding the earth to stay stable at that level. In other words, to orbit, they have to have certain amount of energy. And this energy is also the same as electron orbiting the nucleus. And this energy is called quantized energy ataupun quantum kan, quantum Indonesia bahasa Melayu kan. Okay, and called stationary. Stationary maksudnya dia tetap. Okay, setiap orbit itu adalah tetap. Stationary. Dia ada dua lah, stationary, jangan tersilap lah. T-A-S-T-A-T-I-O-N-E-R-Y. Itu alat tulis. Jangan tersilap lah. Because bila saya belajar bahagian kromatografi, there are two phases. Mobile phases, stationary phases. Bila kita minta student tulis, dia tulis stationary, S-T-A-T-I-O-N-E-R-Y. Saya kata, ni alat tulis cik adik. So, always hati-hati ya. English dia very particular lah. Walaupun English tu sebenarnya is actually scientific term. Dia English also use scientific term. Okay. So, this energy level, okay, which electron reside in order to orbit certain nucleus, okay, it has terms sebagai stationary quantized energy and is labeled as N. Ada sebut N sebagai orbit kan, N starting with 1, 2, etc. The bigger the nucleus is, of course, nucleus consists of proton and neutron. And in neutral atom, proton always equal to electron. The bigger the element is, okay, the bigger the element is, which is the number of proton increase, of course, equivalent with electron number. So you can imagine if the element has, let's say, 30 electron, and this 30 electron must be put outside the nucleus, okay, at the same time, simultaneously orbiting the nucleus without colliding each other, tanpa berlanggar satu sama lain. So meaning that it has to be put into a various stationary energy level, and this energy level dipanggil orbit. Okay, so the higher the energy level, the further the orbit from the nucleus. Inilah tadi Ini 1, 2, 3, 4. This called excited state. This is ground state. See? So outer or further the orbit from the nucleus, okay,
The higher the energy level, yeah, you need more energy here, more energy here, and more energy here. A bigger energy, the further the orbit from the nucleus. Okay, it's written on the 2D, even though into a line. When you put into a circle, just to representing orbit, it become like this. So the bigger, the higher the energy. Okay, the higher the excited state. Okay, second, this is the first postulate from Bohr. Okay, postulate ni macam pemerhatian lah. Okay, pemerhatian. Okay, second thing he said that the atom does not change energy while the atom move within an orbit. Within an orbit. Kalau dia hanya berputar dalam orbit yang satu N1 ni, it has the same energy. Same goes to the, let's say, calcium or helium. Helium two electron, both two will reside in the same orbit. Let's say, other than two electron. So only certain electron will reside in an orbit. So the next electron will reside next orbit. Okay. So the atom does not change energy while the electron move within an orbit. Okay. The third postulate from him, the energy of atom changes when the electron move to another orbit. See, the energy of atom changes when the electron move to another orbit only by absorbing or emitting photon. Okay, because just now Bohr said that in every orbit, the energy resides in that orbit. If the electron want to move from one orbit to another orbit, it has to be excited. In other words, energy must be absorbed. Okay, from here to here, it absorbs the energy, excited, and then because this level is not a ground level state, it becomes unstable, automatically it goes back to the ground state. So while proceed to the ground state, automatically it will emitted a photon, the same amount that being absorbed earlier. Okay, the energy of atom changes when the electron move to another orbit of this level minus amount of this ground level, you can get this amount. So if we do know how much this amount of energy, which is contrast amount of energy, so we know how to supply energy in order to excite or transmit this electron to another level. Okay, so we supply certain amount of energy. For example, here supply certain amount of electricity and produce heat, and this heat up to certain stage we produce light, and this light is actually representing electron that emitted after it being excited to a higher level. Okay, this formula given from him. Okay, E is energy, contrast energy, as I said earlier, is H times mu. Okay, difference between energy atom at the final minus the initial. The general formula is H mu. Okay, can you remember this three postulate produced by Bohr? Just to explain how electron is distributed in an atom. There are only three postulates from him. Okay, much easier to remember kan. Satu, energy level. Okay, second, does not change energy in certain orbit. The third one, if you want to move, you have to supply or you absorb or emit photon. Okay, that's how Bohr described electron in an atom. Okay, let us look at the electron transition. Bohr said that electrons in the first orbit, let's say N1, of course N1 because Bohr already explaining on the hydrogen atom. Okay, so electrons in the first orbit, which is N1, it closest to the nucleus. Okay, closest to the nucleus, and the H atom it is in its lowest energy level. which is called the ground state. Okay. Here, Bohr tried to explain how transition occurred actually. Okay, this is the first electron residing in the inner part of the orbit, and this orbit have its own energy level. Okay, this is quantized energy, and if this electron stable at this state, we can call this as ground state. Electron as this orbit is at ground state. Okay, next, when each atom, hydrogen atom absorb energy, absorb energy to a certain amount, the electron have the capability to jump to a higher level, which is excited level. This is a dotted line. Why he put dotted line? Because actually hydrogen only have one electron. There's no orbit outside. But if this electron being transmitted to another level, this electron will move to higher level and start orbiting the nucleus at higher level. But because of this high level is not actually exist because it's transition state, this electron eventually return to ground state. So at this state, which is called excited state, the first receives energy, being out to the another level. Once they are orbiting the nucleus at high level state, it has its own energy because this energy being absorbed from the outside. Absorbed. So at a certain stage, because this is not stable state, it will go back to the ground state. Return to ground state. So at excited state, electron is unstable. Why unstable? Because this is not actually its own orbit. It becomes unstable. The electron returns to ground state by emitting energy, that is photons, in the form of electromagnetic radiation. Electromagnetic radiation. Energy being released. This is how scientists prove the existence of electron. At that time, only Bohr can prove that there is electron emitting or surrounding an atom. Unfortunately, Bohr can only explain for hydrogen atom sahaja. Kita tengok. The weakness of Bohr atomic model could only explain the spectrum of hydrogen. What is called spectrum? This is spectrum. Light being produced after being emitted, after being excited to a certain energy level, they produce certain color, and this color we call spectrum. Ada cara-cara spectrum kan? There's only certain spectrum hydrogen or ions that only contain one electron. So he tried to prove with another type of atom, helium. Next to it is helium. Helium has 2 electrons. So he removed 1 electron from helium. Helium become He+. So he can easily explain the characteristic of the helium H+ resemble as hydrogen. So helium also have electron, and this electron orbit and produce the same amount of energy if certain amount of photon is absorbed by electron and goes back to the ground state. And also he can only explain for the remove 2 out of 3, it show the characteristic energy same as He+ and also atomic hydrogen. Other than that, Bohr failed to explain all the spectrum produced by each of the electron when they are supplied with certain photon of energy. And then could not predict the energy level and spectra of most atoms that having more than 1 electron. Other than lithium, Bohr cannot explain how this energy level produced, and most of the ion being produced in order to have more spectrum. And then dia kata, the modern quantum mechanics retains Bohr concept of discrete energy states and energy involved during the transitional orbits of orbits he introduced. This is orbit proposed by Bohr. Okay, because he only postulate 1 to 3 electron. So the simple orbit surrounding the nucleus like this. So after Bohr model, so another scientist come up with a new model such as Rutherford dan juga Schrödinger. They can produce layer of electron residing on each of excited state condition without colliding in each of the electron. So they propose another type of orbit to exclude Bohr model orbit. So that's why they use modern quantum mechanics, okay, the concept, okay. So they reject the Bohr's concept, okay, totally reject the circular orbit of he introduced. But a Bohr model is also important to the latest development. Starting from model Bohr, most of the term being used up to now, such as excited state, ground state, photon, okay, apa lagi? Yang tadi semua kan? Stationary state ataupun ground state, still being used, although being rejected halfway because he can only explain only species with one electron. He tried to explain with more than one electron by using helium and lithium ion, but it failed. Okay, check point number 1. State the postulate of Bohr model of hydrogen atom. Senang kan? Tadi 3 tu, postulate. Remember, postulate is not possibility ataupun apa ni kemungkinan tau. This is done but with a limited observation. Lepas postulate apa atas dia. Lastly dia akan become apa? Teori kan, betul tak? So teori, you bagilah apa benda pun, dia akan result the same. Dia tak boleh deny. Yang ni orang boleh deny. About apa ni elektron klorin dan sebagainya, dia tak boleh buat. So they only cover certain limitation. Yang tadilah. So the answer is hydrogen atom has only certain energy level. Always remember, we're talking about Bohr model, they're always referring to hydrogen atom. So when you want to write statement, always use hydrogen atom. Nampak? Jangan guna atom lain. Dia kata apa? Hydrogen atom has only certain energy level. Betul. Hydrogen atom does not change energy level. Betul. Within an orbit. Hydrogen atom changes memories of energy. Betul. Tapi when applied to another type of element that more than one hydrogen, they fail. So that postulate can only be accepted for hydrogen atom sahaja. Okay. Yang ni saya tak cover lah kot lah. Okay. The important things of hydrogen Bohr model ni up to now. So when it comes to Schrödinger dah boleh buat susunan atom, dia panggil configuration electronic. Electronic configuration. Why this electronic configuration is very important? Because bila element tu it has many electrons, it need to be put into a very specific orbit. So when it put into specific orbit, eventually scientists can see in each element, they show the certain characteristic they call sebagai outer electron. They're not focused on the inner electron. Pelik kan? In the beginning, Bohr try to susun elektron, tapi dia hanya dapat susun elektron yang satu je. Sampai 2-3 pun dia try susun, tak boleh. Bukan dia nak menyusun, maksudnya dia kena prove by eksperimen. Tapi bila eksperimen bagi a lot of colours, 2, 3, 4, 5, 10 colour, macam-macam different colours, they fail to explain. When he fail to explain, meaning that he fails to put electron in proper way outside the nucleus in a certain orbit. So after that, scientists start to do their own model. The final model presented by Schrödinger ni, dia dah dapat call sebagai electronic configuration by the help of quantum mechanics. That's why most of the scientists in this area are come from physics. Sebab tu kita panggil chemistry, quantum chemistry semua kan, so from physics. So Schrödinger dah bantu kita menyusun elektron semua, even tu elektron tu beratus-ratus. So they found out that any element, when they follow his rule to structure the electron in a certain atom, they found out that each atom ni dia ada outer electron, and this outer electron lah yang involved dalam kebanyakan reaction, and only this atom outer electron lah being excited, move back, produce plus ataupun minus, lebihan dan sebagainya. Dia akan membentuk ikatan ionik, covalent, whatever, and this is very very important. And based on that, scientists boleh kenal pasti the chemical properties of each element, and then they form into each compound, and then finally barulah tersusunnya periodic table. Okay, and this periodic table, nama pun periodik kan. Sebab apa dia panggil periodik? Periodic table. Pasal apa? Dia berkala kan, bukan kala jengking tu. Periodik. Orang perempuan tahu. Sebab orang perempuan dia ada period. Period dia datang secara berkala. Dia tak datang tiap-tiap hari. Kalau tiap-tiap hari sakit lah dia. Ataupun sebab tu orang dah kahwin dia tahu. Kalau dia 2 tahun kahwin tak dapat anak, dia pergi jumpa doktor, doktor akan cek nombor 1, dia punya period. Kalau period dia irregular, tak tetap, sekejap 30 hari, sekejap 20 hari, sekejap 15 hari, maksudnya dia tak tetap. Nama pun periodik kan, tak tetap, maknanya dia tak subur. Kalau tak subur, susah dapat anak. So that periodic table pun macam tu lah, jadual berkala. Each element disusun dalam kumpulan masing-masing, and each group, it has its own punya properties. And these properties adalah berdasarkan outer electron that has been arranged in a proper way dengan bantuan sains. Dipakailah sampai whatever properties, and then they start to electronic structure, and then dia akan susun dalam periodic table. Dia akan tengok di mana kedudukan elemen tu berada. Saya rasa sekat itu saja kot.
Okay, baik Prof.
Pak Izzah.
Yeah. Okay. Thank you, Prof, for your clear and interesting explanation about these 2 topics. Okay. So now we are open for our Q&A session, question and answer session. So student, do you have any question that you want to address to Prof?
Ada apa-apa nak tanya?
Ada apa-apa nak tanya? Ada yang tak faham lagi ke? Jangan malu, jangan segan.
Kalau boleh jawab, jawab. Pak Izzah pun boleh jawab.
Allah.
Saya tak ajar kod ni lama dah.
Tapi basic lah, foundation.
UiTM 95.
Lama dah tu.
Tapi itu interesting lah. Because fundamental chemistry is very very important to student lah.
True. Okay, any questions, students?
Ada apa-apa nak tanya?
Kalau malu nak tanya, boleh tulis dekat YouTube juga, YouTube Pusat Asasi tu. Kalau nak tanya soalan, malu tanya. Diorang faham kot Prof. Prof ajar hari ni diorang faham. Tak ada soalan. Ada?
Ataupun mengantuk ke, straight dikejar.
Kami lecture 2 jam.
Apa-apa nanti boleh tanya.
Betul. Okay, so if there's no question, so this marks the end of our session. So I would like to thank you to yang berbahagia Prof. Technologist Dr. Muhammad Azlan, Muhammad Ishaq. Thank you, Prof. Thank you a lot, and all lecturers and students for participating in this professorial lecture. I would like to extend my apologies for any flaws during the program. Okay, so we hope that this session will be useful and beneficial to all. Till we meet again in the future, stay safe and take care. Thank you, Prof. Thank you, students, and thank you, fellow lecturers.
Terima kasih.
Okay, terima kasih, Prof. Assalamualaikum. Salam
Sama-sama.
sejahtera.
Thank you, Prof.
Thank you, Prof.
Thank you, Prof.